Welcome to lesson 3.1. In this lesson, we're going to look at real-world situations. Well, actually, we're going to prepare for them by using variables and constants. We want to be able to see patterns. So in the real world, we can model situations based on their patterns. So we want to be able to express a pattern in math and evaluate and solve it. Okay, so here we have a pattern, and there is a video there, and so you're going to look at the different students, but remember the patterns can be described in multiple ways. So for question 2, we were looking at the dots and we're saying how many dots are at each stage. So stage 1 there's 5 dots, at stage 2 there's 4 more, so 9, stage 3 there's 4 more, so 13. And then at stage 4, we need to be able to predict how many dots there would be. So since we're going by 5s, there will be 17 dots. Now the way I do it is I try and get the expression before I get to stage 10. Some of you might want to do stage 10 before you write the expression. So you always want to figure out what stage 0 is. So what happens at the very beginning. And so since I'm increasing by 4, I want to go back by 4. So then my start was 1, my stage 0, and then I'm adding 4 each time, so that's going to be a plus 4n. So you can see the number is the stage, and then the coefficient with the letter, the variable, is the pattern. So my expression is going to be 1 plus 4n, or 4n plus 1. We want to be able to use that expression to answer some questions like, how many dots will there be at stage 20? So I can plug in 20 for n. So 1 plus 4 times 20, which is 81. And then I can answer the question like, what stage will have 137 dots? So I would set it equal to 137. And then solve for the missing variable. So subtract 1 from both sides, 136 equals 4n, then divide by 4 on both sides. So I get n equals 34. Now that's going to be linear because it's a constant increase. So a constant change, an increase or a decrease, by adding or subtracting, that's going to be linear. So next pattern. Again, you're counting. So 4, 6, 8, and so the next is going to be 10, right? I'm going up by 2 for each stage when I'm counting the number of boxes. So then I would use my expression. If I go backwards, it starts at 2, and each time I'm adding 2. So I would plug in 10 for n to figure out there's going to be 22 boxes at stage 10. So my expression is 2 plus 2n, or 2n plus 2. So again, similar questions. How many dots will there be in stage 20? So 20 is going to be plugged in for n, and I'm going to get 42. And then what stage will have 144 boxes? So I set it equal to 144 and then solve for n. Now this stage is a little bit different. So stage 1 we have 2, stage 2 we have 6, stage 3 we have 12. So this time there's a difference of 4, a difference of 6. So the next difference is going to be 8. So there's a couple of ways I know that. 1, I might be able to see the pattern. 2, I might actually draw it out. So draw stage 4 out. If you notice, we're adding a row and a column. So we're adding a box on top and then matching that on the side. Another way to think of it is these are rectangles. So a 2 by 1 3 by 2, 4 by 3, 5 by 4. So this is saying the stage number, and then I'm adding 1 for the height. So I'm taking that stage number and then multiplying it by 1 plus n. So this was 1 times 2. The next one is 2 times 3. Stage 3 is 4 times 3. So that's 12. And those match the number of dots we see for our table. So one expression is n times n plus 1, or n squared plus n. And then I would plug in 10 to figure out the next one. Or you can draw them out however you want. So this is a quadratic pattern. It's also known as geometric. So linear might be arithmetic or arithmetic. Quadratic might be sometimes called geometric. And there's going to be an exponent when we're dealing with the quadratics or geometric. And again, another way to know it's quadratic is because if I go out, the second layer in the pattern is going to be going up by 2s.